Welcome, students. I'm your host and study buddy, and today, well, we're cramming smart, not hard. This is your high-yield exam review explainer. We're taking the massive, kind of intimidating topic of the thermal properties of matter and breaking it down into exactly what you need to know to pass. No fluff, just the core concepts, the critical formulas, and those really common traps that catch students off guard every single year. Okay, let's look at our roadmap to acing those finals. We've got 5 stops. 1. Level 1, essential definitions. 2. Level 2, changes under heat. 3. Level 3, heat transfer laws. 4. High-yield exam topics. And finally, 5. A practice and study checklist. Let's get right into it. Starting off with Level 1, essential definitions. This is where we learn to speak the language of thermodynamics. Now, whatever you do, please don't lose easy points by mixing these two up. Temperature, which we denote with a T, is simply a relative measure of hotness. It's just a condition that dictates the direction heat is going to flow, and in physics, we always measure it in Kelvin. Heat, on the other hand, that's delta Q, is the actual physical thermal energy moving between systems. And because it is literally energy, its SI unit is the joule. Think of it like this. Temperature is the map, but heat is the actual traveler. All right, this matrix brilliantly illustrates the big 3 temperature scales you are absolutely going to encounter on your test. Seriously, memorize this as your quick reference cheat sheet. You need to instantly know the standard phase change points, like water boiling at 100 degrees Celsius, which is 373.15 Kelvin. But more importantly, look at the bottom row, absolute zero. That's the theoretical point where literally all molecular motion stops. It's exactly 0 on the Kelvin scale, which equals negative 273.15 degrees Celsius. Moving on to a formula you will absolutely need to know, the ideal gas law. When you see PV equals mu RT on your formula sheets, don't just stare at the letters hoping they'll make sense. Read it out loud to yourself like this. Pressure times volume equals the number of moles times the universal gas constant times absolute temperature. Knowing exactly how these variables interact conceptually is going to totally save you on those tricky multiple choice questions. Okay, listen up, because this is definitely going to be on the test. Year after year, professors set these little traps, and the most massive common student mistake? Forgetting to convert temperature into Kelvin before solving the ideal gas law. I mean it. If you plug Celsius into that T variable, your answer will be entirely wrong. Oh, and second, lock the universal gas constant into your memory right now. It is 8.31 joules per mole Kelvin. All right, leveling up. Level 2, changes under heat. Let's see how matter reacts. Notice the core decision tree here. When you actually add thermal energy to an object, that matter is forced to make a choice. It's going to either expand its physical dimensions, thermal expansion, or it'll raise its internal temperature, or it will undergo a complete phase change, like melting from solid ice into liquid water. It's got to pick one. And depending on which path that matter takes, you need to know exactly which formula to trigger on your exam. You're going to use specific heat capacity, denoted by S, when the temperature is actively rising or falling. But, and this is key, you must switch to latent heat, denoted by L, the exact moment the object hits a threshold and actually starts melting or boiling. So check out the flat lines here, because this is a classic exam trap. Notice how the temperature rises steadily, but then suddenly it just flatlines, even though heat is obviously still being added. That's because during a phase change, the change in temperature, delta T, is precisely 0. Why? Because absolutely all of that incoming thermal energy is being consumed entirely by breaking the molecular bonds of the material. It's not raising the temperature at all. Now, the really crucial point is how these definitions actually apply to the real world, because professors love using this for short answer questions. Take water's weird anomaly, for example. Unlike most things, water actually contracts as it warms from 0 to 4 degrees Celsius. That means it's heaviest right at 4 degrees, so it sinks to the bottom of lakes, which perfectly insulates the fish in the dead of winter. Crazy, right? Also, water has an incredibly high specific heat, meaning it warms up way slower than, say, sand on a beach. And that exact temperature differential is what creates those shifting coastal sea breezes. Moving right along to level 3, heat transfer laws. Now we're tracking thermal movement. So there are 3 core methods, and they form the heat transfer triad. First, think of conduction like molecular dominoes passing a baton in a relay race. It absolutely requires physical contact, usually in solids. Then think of convection as a whole buoyant crowd moving across a stadium together. This is the bulk movement of fluids or gases. And finally, radiation. Think of that as electromagnetic waves just shooting through space. It's the only transfer method that doesn't need a medium at all. It can travel through a total vacuum. Now, when it comes to the math for conduction, please don't freak out when you see a big fraction. Just read the logic of it. Heat current, which is the rate of flow, equals the material's thermal conductivity times the cross-sectional area times the temperature difference between the two ends, all divided by the distance the heat must travel. So a higher temperature difference or a larger area, that speeds up the heat flow. But a longer distance, that slows it down. Super simple when you break it down. All right, take a deep breath. High-yield exam topics. We have reached the boss level. Okay, here is a guaranteed calorimetry question you are going to see on your final. Ready? If you drop a piping hot piece of metal into a cold, perfectly insulated beaker of water, how do you mathematically find the final resting temperature when both objects finally stop changing? Seriously, don't get overwhelmed by this. Just follow the steps. Step 1, rely on the first law of thermodynamics, the conservation of thermal energy. In an isolated system, you simply set the heat lost by the hot metal exactly equal to the heat gained by the cold water. Easy. Step 2, plug in your specific heat formulas for both sides. So mass times specific heat times the change in temperature for the metal equals that exact same formula for the water. From there, you just use basic algebra to solve for your final equilibrium temperature. You've got this. Next up, lock this summary table into your brain for the multiple choice section. These are the 3 core laws you absolutely must differentiate. Use Wien's displacement law when a question asks you to find the cosmic temperatures of stars based on their color wavelength. Use the Stefan-Boltzmann law when you're calculating the total radiation energy emitted by a body. And use Newton's law of cooling to explain why a super hot cup of tea cools incredibly rapidly at first, but then slows way down as it gets closer to room temperature. Okay, we're almost there. Practice and study checklist. Let's do some final preparations. Honestly, take a screenshot of this right now. Before you close your books tonight, I need you to verify 4 things. First, make sure you can automatically convert any temperature to Kelvin without even thinking twice. Second, recall that temperature flatlines, meaning delta T equals 0, during literally any phase change graph. Third, clearly define the 3 transfer methods for yourself: conduction, convection, and radiation. And fourth, make sure you can comfortably set up a heat lost equals heat gained calorimetry equation. All right, now that you understand how thermal energy fundamentally drives the physical world, I want to leave you with this final provocative thought to ponder. If thermal energy always flows from hot to cold until ultimate equilibrium is reached, what is the ultimate fate of our universe once everything everywhere finally settles at the exact same temperature? Think about that one as you study tonight. Good luck on those exams, you're going to crush them, and keep asking the big questions.